Okay, so hi, I'm Garret. I'm from Google Fonts, and at Google Fonts, I'm the tech lead of production and standards.
And I'm Rod Sheeter. I'm the tech lead and engineering manager for Google Fonts. So today we're going to talk a little bit about progressive font enrichment, which is a potential solution for speeding up font downloads on the web. And I also want to sidetrack to mention that keep an eye out in the hall for cool swag that Googlers will be handing out throughout the remainder of the day. So to frame the discussion, I want to talk a little bit about what's wrong with fonts on the web today. So I think perhaps not so much in this room, but in general, people believe that fonts just work. And it's not so true. It's a lot better than it was. 5 years ago, maybe, people did things like publish images of text, which was horrible. Machines can't understand it. It's slow. It's got so many downsides. Can't even begin to mention them. So today, at least, we see people using Unicode fonts all over the web. It's pretty ubiquitous. Unfortunately, the delivery is suboptimal. So there's three main ways that people deliver fonts on the web. They either send you the entire font, they break it into little pieces and send you little pieces, or they just build something of their own in custom code. And they all have fairly significant downsides. So we'll look at each one in more detail. So the first approach, you send the entire font. It's super simple. You say, download the entire font, probably is a WAF 2 these days. Next slide. If the page is using the font at all. That's really cool. It's how fonts were supposed to work. Sorry, thank you. You take the font, you stick it on a server, it just works. The problem we run into is that most real pages use only some subset of the characters in the font. So downloading a whole bunch of characters you're not using delays the page showing up. Maybe you see blank text, maybe you see the wrong font and then it flickers and turns into the right font. And it gets worse if the font is a really nice font that supports a whole bunch of scripts, has lots of characters, this type of thing. And the user's really kind of paying for more than they're using. So that you're seeing a couple hundred characters, and in the worst case, you're paying for 10,000 characters. So fixing that's kind of the focus of this entire talk. We'd like the users to basically pay for just the parts of the font that they're using. That is, the parts that they're actually seeing drawn on the page. So next approach that we take is we can fragment the font in little pieces. So we can tell the browser you should download the Cyrillic bit. Next slide. If you're using any of the Cyrillic characters. And you should download, next slide, sorry. You should download the Latin bit if you're loading any of the Latin characters. And the browser actually does most of the heavy lifting for you. It intelligently chooses to download either Cyrillic or Latin or nothing based on what's on the page. So that's really cool. It's a step towards what we want. We can even push this a step further. Sorry, next slide. So we can deliver CJK by cutting a font into a whole lot of pieces, and the browser will actually intelligently pick some subset of them to download. We use this extensively on Google Fonts today. It's dramatically better for our users in terms of rendering performance than delivering the whole font. And it's really simple for the user. And in this case, by the user, I mean the web designer. They just say, I want to use this Japanese font, and it just kind of works and is performant. And that's really cool. But it has some fairly significant downsides. So if you have ligatures, kerning, or layout rules of any kind that span fragments, they just break. So we're damaging the rendering fidelity of the font, which is not good. If we carefully pick how we segment the font, we can minimize the damage, but it's very hard to eliminate it completely. So font fragmentation ends up working relatively well for fonts with large character sets that tend to have few layout features. And it doesn't work tremendously well at all for fonts that make extremely heavy use of layout features. So think Indic and Arabic as maybe examples that wouldn't work so well. So having run into this, the next solution that people come up with, including us, we should just write our own font loader. We'll do something along the lines of have some code, it'll look at the characters on the page, it'll download the right parts of the font, everything will be wonderful. And it actually does work, but it also has some major downsides. So the first downside is that it's pretty complicated. You have to write some moderately thorny code. You tend to break browser caching, particularly if you want to cache the same thing across multiple sites. And it's fairly common that you have a heavy initial load where you need to fetch initial JavaScript, a skeleton of a font, some sort of thing to bootstrap the whole process. So that leaves us kind of unhappy. None of the ways we can load fonts work for us. We have these alternatives, but they're all unsatisfactory. And also, the scale of web fonts is kind of staggering. They're on billions and billions of pages across millions of domains on the web. So that kind of scale justifies making a pretty serious effort to do better.
All right, so given all the problems with font loading on the web today, what can we do to make things better? The answer is progressive font enrichment. The basic idea behind it is this. Look at all of the code points in use on a given page, get a subset of a font for those code points, but unlike traditional subsetting, we're going to merge the subsets from several page views into a single font. On each new page, we only need to get data for characters that have not yet been seen. The merged font is reused across page views and across domains. Over time, the full original font is built up. The system would be built into browsers and widely available for use without needing heavyweight JavaScript libraries. Let's illustrate with an example. Say I look at a page which contains the text meows rendered in with a web font. I could compute a subset of the font needing just the characters from meows and load that font. So far, so good. However, if I go to a second page that has the text awesome rendered in the same font and try to reuse the subset from the previous page, it will be missing data for some of the characters, specifically the capital A and lowercase w glyphs. And the kerning rules for capital A and lowercase w is not in this subset. Using progressive font enrichment, we can solve this by loading a small additional piece of data which contains the missing glyphs and kern rule. It's merged into the subset from the first page to produce a new version of the font that contains everything we need. Progressive font enrichment has many benefits. The most important is that you're only paying for the font data that you're actually using. Most existing web font loading solutions inevitably end up sending more data than is needed for a page. In general, smaller font loads mean faster rendering times, which is a good thing. Our current implementation at Google Fonts for CJK serving can trigger several font loads within a single page to get all of the needed pieces. With progressive font enrichment, you could get everything with just a single request. Unlike with Unicode range, we can also preserve layout features across the font to maintain correct rendering. And because it's implemented natively in a browser, no heavyweight JavaScript client needs to be loaded before font loading can begin. Lastly, a native implementation should also run much faster than something written in JavaScript.
All right, so I feel like at this point it would be fair to ask, who is this going to benefit? Is it only a solution for CJK or is it general purpose? So to reason about that, we're going to kind of break the world scripts into three crude categories. We're going to say that more or less, we're going to think of things as being either simple scripts or complex scripts or very large scripts. And we'll take a brief look at how progressive enrichment would play out for each of these groups. So first up is simple scripts. You think Latin, Greek, Cyrillic, this type of thing. We'll characterize them as having relatively few glyphs, think hundreds, and relatively low reliance on layout features. And generally speaking, the text is going to be legible even if the layout features fail. Even in these scenarios with a smaller character set, it's quite common that a given page is not using all of the characters, particularly if you have a font that supports a whole bunch of simple scripts. So we can fragment simple scripts, which does allow things to load faster. So in that case, maybe we break Cyrillic and Latin into different pieces, but then we damage rendering fidelity. So progressive font enrichment here eliminates the need to trade off speed and quality. We get to have fast rendering and correct rendering. So complex scripts we'll define as ones that are pretty reliant on layout rules. We'll say that typically if you smash all the layout rules, the page is significantly less legible, maybe illegible. It remains common that a page will not use all the characters on any given page, so it feels like there is potential to send only the part of the font you're using, but with today's technology, it's a bit harder to take advantage of that, particularly with Unicode range. For example, if we take Arabic and we just smashed into tiny pieces, we've basically destroyed the result. So Google Fonts today, we deliver the entire script in a single block. So for example, you download all of Arabic if you're displaying 2 words in a title. That's kind of suboptimal. Indic is even more complicated for us because we have things like characters that exist in multiple Indic scripts. So potentially you want to display a 1-word Indic title, and we have to send you 5 or 6 Indic scripts, which we currently deal with by just avoiding fonts like that, which, again, not entirely optimal. So here we see exactly the same benefit. We avoid speed-quality trade-offs, and we get to have fast loading and correct rendering. So last of all, large scripts. We'll define them as being ones that probably have something like tens of thousands of characters. Generally speaking, fewer layout rules. Think Chinese, Japanese, and Korean. On any given page, we typically see a pretty seriously small subset of the characters in use. And there's an extremely strong bias towards a small set of highly used characters. Any given page is probably going to use a bunch of high-frequency characters and a couple from the long tail, so you can't just send the high-frequency ones. This is where fragmenting the font really shines. You can reduce download size by, say, 90% versus delivering the whole font, but it damages rendering fidelity, and it's actually quite complicated to own and operate. So in order to make that work, we had to analyze millions of CJK pages, look at the character usage frequency, use that to try and figure out our strategy for how we were going to cut things into little pieces. If you were at ATypI last year, you might have seen some of our teammates give a talk about it. So here again, we would see that progressive enrichment would avoid trading speed and quality. And maybe we get an actual additional benefit that it would be a lot easier to just own and operate. Next up, variable fonts. So we're seeing more and more use of variable fonts on the web. We always hear people say that they're smaller, but that's kind of seriously lacking in nuance. Adding an axis can easily double the size of a font. Adding another one might double it again. And that means that the variable font is only smaller if you're using a lot of styles, and that the user has to have a really sophisticated understanding of it, which they generally don't actually have. So they're not that easy to drive either. So kind of speculating wildly, what if progressive enrichment could intelligently deliver you only the parts of the variation space you're using? That would deliver all the same benefits for variable fonts, and that would be kind of cool. So let's take a look at an example page just to try and illustrate the point. So on this page, we're using 4 fonts. We're using Noto Sans JP, a couple of weights of Roboto, and YouTube Sans. But we're not using very many of the characters from any given one. And Noto Sans is probably the most extreme. It has over 10,000 characters, and we're using maybe a couple hundred. So downloading only the characters we need would be a huge win. And if we look at the web in general, progressive font enrichment basically improves font loading in almost all cases. It seems to span scripts. Everything just renders faster and more correctly. So end users end up paying only for what they actually use. We think that's a really compelling pitch, so how do we make it happen?
All right, the good news is that development and standardization of progressive font enrichment is already underway. In order to get progressive font enrichment widely adopted, standardization is needed. That is currently being handled by the W3C Web Fonts Working Group. The working group is the standards body responsible for web font technology, and you may know them from their previous projects, WAF and WAF2. It's a cross-industry collaboration that has participants from a broad array of companies, including browser vendors and font technology companies. The goal is to standardize technologies that allow the interoperable and efficient deployment of web fonts. Earlier this year, the group was rechartered with the goal of creating a standard for progressive font enrichment. So far, 2 different approaches to progressive font enrichment have been proposed. The working group is now evaluating those approaches to decide which to standardize. The first approach we call Smart Server Simple Client. As its name suggests, in this approach, the server handles most of the complexity. The basic idea is that the client asks for a set of code points in a font, and the server computes a patch that the client can apply to their local copy of the font to add those characters. In this model, the client has no need to understand the specifics of the font format. It just applies a standard binary patch to their existing font file to create an extended version. The second approach, which we call Simple Server Smart Client, does the reverse. In this model, the client understands the font format. It figures out which parts of the font are missing and requests them from the server's copy of the full font using HTTP range requests, which let the browser request just a segment of the file. The server in this model can be any standard HTTP server, which supports range requests. No extra logic or server-side code is needed. Both approaches have their advantages, but what are some trade-offs for the 2? For Smart Server, the client stays quite simple. It doesn't need to understand font format specifics, and hopefully this will ease adoption by browser vendors. Since the server handles complexity, it can be updated and optimized over time. New patching and compression techniques can be instantly deployed to end users. For Smart Client, you only need a standard HTTP server, which will make adoption by font hosting providers easier. Self-hosting fonts in this model is also quite a bit easier. There's also some interesting differences in the request and response sizes between the 2 approaches that favor one model or the other, depending on the specific situation. Both options look promising, and there's currently no clear winner between the two. This is a good thing. We can race the two solutions against each other in order to figure out which one works best. By testing both, we can learn things from each approach that can be incorporated into the other.
All right, so we have multiple proposals, but we need to get to the point where we have just a single winner. So we need to stop and think, well, what do we want from a progressive font enrichment system? Okay, well, it shouldn't damage rendering fidelity, so the page should look exactly as it would if you had the entire font available locally. It should download data fairly, so you should download only the parts that you're actually using on the page. We should minimize the user-perceptible delay caused by font loading. And we should have good network performance, so minimal data transfer and an acceptable number of network requests. And we want all this to work for any page and any script on the internet under a wide variety of network conditions. So the good news is that actually both proposals seem like they're going to achieve all this. So that's great. The bad news is that makes picking a winner harder. So our plan to deal with that is to try and simulate. So we're going to try and simulate realistic user browsing under realistic network conditions and see which proposal does best. So we have data about the latency and transfer rates typical of real-world networks. We need a data set that describes realistic user browsing. So we need something that describes kind of how the user goes through a sequence of page loads and what code points are being rendered on each page so we can simulate actually loading. If we had those things, we could put together a pretty good simulation of how each proposal would work and use that to pick a winner. The problem is that we need that data set of browsing session data, and we don't have it. So creating that data set and rigging up the simulation is really the next big step for this project. And once we've got that all done, then we can pick the winner.
All right, let's look at what the future looks like for progressive font enrichment. First off, standardization is hard. It's a long process that's going to take some time. As an example, WAF2 took multiple years. And currently, we're still in the very early stages. But here's an overview of the major phases we'll be undertaking. I'll talk about them individually on the next few slides. The first phase is analysis. This is where we currently are. The goal is to gather proposals for solving the problem, design and build an evaluation framework that can be used to benchmark and test those proposals. This will allow us to make a data-driven decision on which approach to standardize. Next, based on the results of the analysis phase, an evaluation report will be created that recommends which solution we should proceed with. With the solution selected, the next step is to author a detailed specification that describes how the solution will work. It is what allows interoperability. As long as each implementation follows the specification, all of them should be able to work together. With the specification completed, implementation can begin. The W3C requires that 2 independent implementations are created. These should be written based on the spec, and their purpose is to prove that it's possible to create an implementation from the spec. These may end up as beta or canary features in browsers, which is what happened with WAF2. Finally, with specification and implementation created, the new technology can begin wider adoption. Ideally, at this point, browsers will begin shipping clients and font providers will begin providing support for the fonts they host. We created a demo of one approach to the progressive font enrichment. You can find it at this URL up here. The demo compares the amount of data needed for font transfers using a few different methods of font loading, one of which is progressive font enrichment. All right, thank you for listening.